Okay, so let's go over this quick. If you have questions, please make me do my job. So stop me and say, "Whoa, Mr. Lindenberger, you got to explain that. That doesn't make sense to me." Okay. With magnets, magnets and electric charges are similar to one another. With electric charges, you have a positive charge and a negative charge. With magnets, you have a north pole and a south pole. Really, what it is, it's really a north-seeking pole and a south-seeking pole. But because we are lazy people, we abbreviate that to a north pole and a south pole. But keep in mind, it really is a north-seeking pole, a south-seeking pole. Why does it have that name? Because if you have the Earth and you were to hang your magnet, yesterday you guys should have had this thing. If you were to hang your magnet, you'll notice it's always going to arrange itself a certain way because one side is the north, one side's the south. Okay? But the Earth, by the way, stupid lights, hang on. Okay. The Earth, by the way, the reason that the north-seeking pole seeks out the north is where Santa Claus lives at the North Pole, there's actually a magnetic south pole there. Okay. If you go to the penguins in the Antarctica, there's actually a magnetic north pole there. The Earth's magnetic field, by the way, is not constant. We are currently in a time period where the Earth's magnetic field is getting weaker, which potentially is bad news because the Earth's magnetic field does do some really important things. Protects us from bad radiation coming from the sun. By the way, that's what the northern lights are. That's the bad radiation getting trapped by our magnetic field. There, in the Earth's history, there's been cases where the Earth's magnetic field has flipped. Okay. But anyway, everybody got that? Okay. All right, magnetic fields. Okay. Magnetic fields point in the direction that a north pole would go. Just like when we did electric fields, they pointed in the direction that a positive charge went. So magnetic fields point in the direction that a north pole would go. So guys, some of you were messing up your pictures. Okay, I already saw, hey look, here's my bar magnet. If I put down a north pole here, it's going to move away. If I put down a north pole here, it's going to loop around and go towards the south. If I have a horseshoe magnet, it's going to point away from the north towards the south. Couple things that I want to make sure you guys have. The symbol for magnetic field is going to be a B. I have no idea why they chose a B, but they did. Okay, it's going to be, so like when we talk about B fields, we're talking about magnetic fields. The more field lines you have, the closer they are together, the stronger the magnetic field, just like when we were doing electric fields. And then the other thing I want to keep in mind, I want to make sure you guys understand, magnetic fields are really loops. So inside my bar magnet, my magnetic field actually points this way because it is completing that loop. Okay, is everybody doing okay with that? And then when two magnetic fields interact, you get a force, meaning you're going to get attraction or repulsion. All right, how am I doing? Everybody okay? Questions?
For the horseshoe magnet, where's the stronger part?
Again, near the poles.
Okay. And that's just because you're closer, so you have basically more potential to travel towards the other pole. Right?
Correct. Yeah.
Okay.
Yeah, it's very similar. Do you remember when we were doing electric fields around charges? If we were to say where's the electric field the strongest, it was near the charge. Why? Because that's where the field lines are closest together. Okay. All right. Magnets, magnetic fields. We okay?
I'm still a little confused on the Earth, why the South is on top, I guess.
Well, the reason that the South is on top is just because when the Greeks were really the ones that kind of like discovered, if you like, what a compass, and they realized that they held up certain rocks that were called lodestones, and part of the rock would always face the north. So they called it the north-seeking pole because it was seeking out the north. Part of the rock would always seek out the south, so they called it the south-seeking pole. The Greeks didn't realize the reason that happens is the Earth has a magnetic field, and there's a south magnetic field at the top.
Oh, so the compass is, when it's pointed north, it's actually seeking out the south. But, okay.
Right. So really what's happening, if we were to draw the magnetic field around it, do you see how that compass is just lining up with the Earth's magnetic field?
Yeah, that makes sense.
Okay. Thank you for the question. Anybody else? Okay, magnetic fields, we're good? Okay. The other thing you learned about was magnetic domains. So let's talk about that. Let's make sure it makes sense. Okay. Magnetic domains are clumps of atoms that line up magnetically. Okay. Materials that can be magnetized, for example, your nail that I gave you, for example, your paper clips that I gave you, okay, have these domains. Okay. Materials that cannot be magnetized, for example, stainless steel. If you try to put if you have a stainless steel refrigerator, magnets don't work on it. Okay. But another example would be aluminum, glass, wood, insulators. Those cannot be magnetized. Okay. So far, so good? So if I wanted to represent this, if this is your nail, does everybody have your nail someplace you can find it? Okay. If you have your nail sitting by itself, there's your nail. Okay. This nail, if I try to pick up some paper clips, it's not magnetic. Okay. You can see it's not going to pick up any paper clips. Okay. But the reason that happens is if all of these little things represent the domains are all mixed up. Okay. Where if you have your magnet, so here's my magnet. We'll pretend it's a bar magnet, so it looks like this. Here's my bar magnet. Okay. But inside here, there are domains that are going to be lined up. Now, which way they line up, they're going to line up with the magnetic field. So remember, if you were to draw this, okay, the magnetic field points away from the north, like this. It points toward the south. But remember, it really is a complete loop. So the domains, if I want to draw them inside, would I draw my arrows pointing left or pointing right?
Left.
Because then it's going to complete that. Does everybody understand that okay? By the way, a stronger magnet just means the domains are more lined up. A weaker magnet means the domains are less lined up. Okay, does everybody follow that okay?
I have a question.
Go for it.
So is the reason that the iron doesn't, like, it can't permanently magnetize, but then the, like, actual magnet could permanently magnetize, is that just because the material is, like, ferromagnetic? I think that was the word.
So what happened with magnets, okay, like a permanent magnet like this, when they were making it in the factory, they melted the iron. Most of these are just iron. They melted the iron, and while the iron was cooling, they put it in a really strong magnetic field. So as the iron is cooling, the domains cooled lined up. Hence, you have a bar magnet. Where for a nail, because, hey, I don't really want this thing to be magnet, there's no reason for me to want it to be magnetized, they just had it cool normally, which the domains are not really lined up. Does that make sense, Navia?
Yeah, that makes sense. Thank you.
Okay. So here, guys, if I take my nail and I stick it to here, you'll notice that my nail becomes magnetized. You can see that. Okay. In fact, if I take this off you can see it holds on to a little bit of its magnetism. So when I do that, I want you to figure out, like, draw what this would look like and make sure you understand why. Okay, so let's just make sure we understand why. You know, we already said these are going to point like this. So what's going to happen, I want to make sure you guys understand, it's going to force these domains to line more up like this. So now these domains are going to line more up like this. Which is why my nail becomes magnetized. And then when I take it off the magnet, you can see it still holds on to a little bit of its magnetism. That's because the domains are still lining up a little bit. If I drop this, and then I try to pick up paper clips, it doesn't work because I'm knocking those domains back out of alignment. Because remember, the domains didn't really want to be lined up because when it cooled, they were like this. Does everybody understand the difference between, that makes sense? Questions? All right, are there any questions from what we did yesterday? Is there anything else I can help you with? All right, then here's what we're going to do today. You are going to take your compass. Take your compass, put it down, please. So here's my compass. Make sure. Well, that's not very good, is it? Let me see if, does that, that's better. You can actually see it now. Okay, so I want to make sure you guys understand the magnetic field in the room is pointing that way. That would be the Earth's magnetic field. Does everybody follow that piece okay? Okay, that's why my compass lines up that way. Okay, which, by the way, that way is north. Okay, I'm facing where I am, you know, that way is the football field. Okay, that way is north. But I want to show you something. So we're going to take out your wire. Okay, I got my wire here. You're going to take your battery. Okay, I got my battery here. Now, if you bring this close to the compass, because this thing is a big chunk of iron, do you see how that's attracting my magnet? So don't have it too close to that. But what we're going to do, now guys, we're going to hook up the ends of your wire to the battery. Don't leave it hooked up very long because it's going to get hot. If it starts getting hot, let it go. Don't be like, oh, it's getting hot, it burns! Just let it go. Okay, so, but what I want to show you is that if you have current flowing through this wire, you can deflect the needle. You can deflect the compass needle. So what I'm going to do to get current flowing through the wire is I'm going to hold it like this and hold the other end like this so that I can hold it with one hand, okay? And then I'm going to bring this close. And when I bring this close, you can see I can deflect my needle. Does everybody see it? And then I'm going to take it off so that it's starting to get a little bit warm. Can everybody see that okay? Come on, that's cool stuff. Like, that is super cool stuff. So let's talk about that and make sure that it makes some sense. So this is going to be some new notes you're going to take, okay, everybody? New notes here, okay? Okay, moving charge, which is current, is going to have a magnetic field around it. Did everybody see how we proved that using your wire and your compass? When you guys are done with the wire, like, make sure it goes back in the bag because we're going to need it later. Okay, so like, you know, make sure you get same thing with your compass and stuff. Don't be losing stuff. Okay, make sure it goes back in the bag. Okay, I want to show you guys, okay, what the shape of the magnetic field is around there. So I have an apparatus. Let me just show you this apparatus. So here's my apparatus. Okay. So what is happening? Well, let me see if I can do it like this. Okay, just so that, okay. So I have a wire here, okay, that I'm going to hook up to a battery using this clip right here. And then the wire comes up over here. I want to show you, if I connect this, watch these compasses here and see if you can tell what shape it forms. So, like, just so you know, I have a big battery. I don't know if you guys can sort of see the battery right there. But watch the compasses over here. So watch when I connect. Can you guys see how it forms a circle going around? Does everybody see it? Watch again. Can everybody see how those compasses line up in a circle going around? Does everybody see that? Okay. So that moving charge, okay, a current carrying wire has a magnetic field around it. Okay, that is circular. Okay, it's a circular shape. So if I was going to try to draw this, if I have, there's my current carrying wire, the magnetic field would literally look like this loop going around it like this. But here's the problem. Here's the problem is that this is a 3D thing and my paper is 2D. So we need to be able to represent a 3D thing on 2D paper, okay? Okay, we need to be able to represent vectors that point out of the page versus vectors that point into the page. So if we have a vector going like this, here's my pencil, pointing in versus pointing out versus into the page. Now, by the way, guys, if you have your handy dandy, fancy pants, representer here, okay? If here is your page, out of the page is the plus Z direction. Is everybody okay with that? This would be the plus X direction. This would be the plus Y direction. Is everybody okay? So when we say out of the page, that would be the plus Z direction. If we were going to say into the page, that would be the minus Z direction. Does everybody follow that okay? Questions so far? Everybody doing okay? Whenever I tell my wife that I'm teaching about vectors, she always gets annoyed at me, and she always says, well, why don't you just call them what they are? They're just a bunch of effing arrows. And I'm like, no, honey, they're not just a bunch of effing arrows. Their vectors are represented by arrows, but they're not just arrows. And she's like, no, they're just a bunch of effing arrows. Well, we represent vectors by arrows. So if you think about an arrow, if I was to draw an arrow, the arrow has the point on it, and then there's typically like the feathers on the back. You guys with me there okay? Well, if I have something that's pointing, if I have an arrow that's coming out of the page, so like you're looking down on it, and you look down on that, what you're going to see is just the point. So this is actually a direction. That means out of the page. because that's the point of the arrow. Does everybody, you guys writing this down? Does that make sense? Where if it's into the page, you're going to see the back of the arrow. Well, the back of the arrow is going to be those feathers. And that would be represented by an X. So an X is going to mean a dot means out of the page because that's the point of the arrow. And an X is going to represent into the page. Does everybody follow that okay? So we now have a way to show different ways. Like, hey, that's positive Y. That's negative X. This is positive Z direction. You guys with me? This would be the negative Z direction. So these are all different directions that we could have. But we need to include this for that reason, because we're trying to represent that 3D model. So far, so good? All right. All right. Current carrying wire has a magnetic field around it. It is a vector. So remember, just like electric field, magnetic fields are vectors. That means you have to worry about magnitude. And you're going to do a short little simulation today to figure out how do we find the magnitude. And then you also need to know direction. And that's what we're talking about right now. To find the direction, we're going to use what's called the first right-hand rule, which a lot of times I'm just going to rewrite it like that. Now, to do the first right-hand rule, guys, I know this is going to be confusing for some of you. You have to use your right hand. Okay, if you use your left hand, you're going to get the problems all wrong. You have to use your right hand, both figuratively and literally. Now, if you are unbelievably gifted like me and you write with your left hand, you can do the right hand rule and write at the same time. For you poor schmucks that write with your right hand, you are going to have to put down your pencil, do the right hand rule, pick your pencil back up, and write the answer. I know you're going to lose precious seconds. Blame your parents. Okay, but you have to use your right hand. Okay, when you're doing this, okay, your thumb points in the direction of the current. And remember, guys, when we're talking about current, we're always talking conventional current. Okay, so the direction that positive charge is going. Okay, when you do the simulation, the first thing it says to do is click on conventional current. So make sure you do that. So your thumb points in the direction of current. So like if we had a wire going this way, you would take your right thumb and you would literally put it like that. Is everybody with me there okay? This is easy to remember. Why? Because there's one wire and you have one thumb. Okay? Your fingers will curl in the direction of the magnetic field. Okay, this is easy to remember also. Around a current carrying wire, there are many magnetic fields. You have many fingers. Current carrying wire, magnetic field. Now I want to caution you, you're not going to make a fist. you're going to curl your fingers. Is everybody with me there, okay? And unless you're some weird freak of nature, your fingers will only curl one way. Okay, like, no, that doesn't work. Okay? So that's why we have to use our right hand. Is everybody with me? So if I was doing this one, you guys are going to do this with me. Okay? On your paper, okay, you are going to take your hand and put it right on top of here. And then you're going to curl your hand just like I'm doing. Do you guys see above the wire? Do you see which way your fingers are curling? Is that into the page or out of the page?
Into the page.
Is that a positive Z or a minus Z direction?
Negative.
That would be a minus Z direction. Is everybody with me? So if I wanted to represent that, is that a dot or is that an X?
X.
Those would be X's. So above the wire, I would have X's. Does everybody understand that? Okay. Below the wire, okay, you're going to have to turn your hand, okay? But if I turn my hand, here's the wire, and you can see my fingers here. My fingers are curling out of the page. So then I would have dots down there. How am I doing? Is everybody okay? So the magnetic field would be coming out and then looping back in. Coming out and looping back in. All right, I want you to try one more. Let's say we have a wire that is situated like my pencil, where the current is coming out of the page. Okay, so here's my wire, and the I is in the plus Z direction. Is everybody okay? Okay, so put your hand right like this, because that's which way the current's going, and then curl your fingers. Curl your fingers around. Do you guys see what shape is it going to sweep out?
Circle.
A circle. And then will I make the arrows so that it's going around clockwise or counterclockwise?
Counterclockwise.
You got it. So this type of question would be like, hey, you have a wire like here. Directly above it, which way is the magnetic field pointing? Oh, it's pointing to the left. Or you could say it's pointing in the negative X direction. Does everybody follow that okay? Okay. All right. That's my intro. Is everybody good? Questions?
Where does this come from? Like, why is it in that direction?
It is.
Okay.
It's kind of like saying, why does the gravitational field point towards the Earth? Because that's which way it does.
Okay.
Yeah, I mean, I know that's not a super satisfying answer, but it just does. Okay.
So someone just thought of the bright idea to use their hand.
Right, to help you represent it. That's where this came from.
Okay, thank you.
Yep.